Hello everyone. In this session we will understand basis expansion. This is the last chapter for the course machine learning. Um, Actually this topic is not into the machine learning. It is the topic for data science. However, still we will understand it. It is somehow more mathematical, more analogical, but we'll try to understand it. Well, to understand this expansion function, you need to be very fundamental with your regression and classification topic. Okay, so if I have a regression as well as classification problem, the general thing to solve it is generally we use linear model, right? We generally use linear model to solve these classification and regression problem, right? So I will write to solve it we use linear models. And why I am using this linear model? Because it is easy to interact. They are easy to interact, easy to implement. Actually, they are easy to interact versus, or sorry, slash implement, and it is necessary. Okay, we don't have any other thing other than these linear model necessary for the with scarce data, with with scarce data. Okay, because if I have a larger data set, then if I use non-linear model, then the model is going to be very complex. um, Even if I don't use these non-linear model, actually non-linear model itself is a very complex technique. They are very complex methods to use non-linear model. If I have a huge data set, and then on that if I'm using non-linear model, then even then it is going to be very complex. Why? Because itself your nonlinear model is nonlinear functions or techniques are actually very complex, and if you are applying that techniques inside the huge data set, then again the whole thing is going to be very complex. So to use such model, instead of that I can use a linear model which is simple to interrupt. I can easily solve it, and that's why I'm using linear model to solve these regression and classification, because it is easy to understand. And if I have a larger data set, then the first priority or the first thing that comes in my mind is the linear model itself. So this is kind of necessity with my huge data set, right? So the first is easy to interact and necessary with scarce data set, and third is also there that uh, I mean it gives you it gives you better result. It gives you better result without overfitting. Okay, I mean it gives you some proportions of overfit, but let's say compared to non-linear model, it gives you a small range of overfit model. So these are the three criterias on which I'm putting my linear model to solve these regression and classification problem. Um, well, but for the basis expansion, the data scientist, what it says that there is still a competence power. If you want more accurate result, then you need to move beyond the linearity. Okay, so non-linear model are very complex, but they have component power to increase the accuracy of your this model. Okay, even though linear model are easy to understand, and non-linear model are complex, cannot implement it in a very simple terms, but the power of increasing the accuracy of your model is there with the non-linear model. So if you increase this, if you move beyond this linearity, then you can increase the result of your model. So what I mean to say is, if I write here, we can achieve greater result if we move beyond linearity. Okay, linear, oh I'm so sorry, Oh, I had done some mistake, I think. Oh yeah. So this is linearity. I'm somehow confused with this term. So we can achieve this greater result if we move beyond the linearity. Okay. So what I mean to say is, how can I move beyond linearity is nothing but to use non-linear model, but with some constraint. Okay, you cannot use the pure non-linear model. I mean, you have some constraint to use it, but we are going for non-linear models. So actually what I mean to say is, I'm going to some higher dimension space rather than to go in lower dimension space. In your unsupervised learning, I had told you that we have to move from higher dimension to lower dimension. However, in this chapter, this is a data science topic, so we are we actually move from lower dimension to higher dimension, but still we have to stable that higher dimension space with some constraint. Okay, that is what I meant to say here. You will understand what I actually want to interpret over here. So let's say I have a graph looks like this, and this graph is easily separable if I have plus points over here. These are the these are the data points, nothing else, and I have a minus sign over here. These are the thing. Okay, and let's say I have a little outlier over here, and I'm going to draw it with a negative sign over here. So this is my outlier, and this is the outlier for this quadrant. Okay, now and let's say I have a decision boundary passing like this. This is my decision boundary of SVM. So this is the decision boundary that separates your positive cases and negative cases far apart from each other. Okay, but if you see this graph, then your linearity is fail over here. So the separability, if I want to say, is that linear separability failed. Why? It is not just because of these two outliers, but however, if you see the real case, the real scenario, if you have a huge data set, then in that data set we don't have these two outliers only, we have many numbers of outliers that come in others quadrant. So because of that, the linear separability failed here, sometimes failed. Okay, so I just want to write here sometimes failed. And because of these plus and minus point, these plus and minus sign data point, I'm saying that it is failed over here. And we can actually separate it in a very simple terms if I use something called as soft marginal technique. Okay, if I use soft marginal technique, then basically I can resolve this outlier. Okay, I can resolve it. So I just want to write it over. Resolve it by soft marginal technique that you can use. Okay, this is easy. I mean, there are only two outliers, and I can separate these out with the help of some soft marginal technique. This is a small linear model right now here. Now let's say if I have something far beyond this. Okay, if I have if I have a non-linear decision boundary, this is a linear decision. The earlier example was an linear decision boundary. However, if I say if I have a data set looks like this, let's say my minus signs are, they are separated like this, scattered like this, and if I let me change the color here a little, and let's say these are the plus points that uh, something like this, and let's say my decision boundary is now looks like this, and you can see this is the parabola decision boundary. It is a non-linear function decision boundary, and they are non-linear, right? Okay, I hope you understand it. So this is a parabola, and this is a decision boundary, looks like a parabola, or when I say parabola, it is nothing but a quadratic function that I had applied over here. I hope you understand what you mean by quadratic function. So this is the decision boundary that I had used. And now how can you separate this? The question is how you can linearly separate it out. I hope you are getting the question, that if I have this higher dimension decision boundary and you want to separate it with linear decision boundary, I mean, you understand, a higher dimension to get into the lower dimension, how can you do that? Well, actually there are ways to do it. If you see the data set itself here, then there are we can say that this is, if you look this data set into the 2-dimension, right, if you look this data set in a 2-dimension, then I can say that it looks like this, because I only have two separate data points, this plus and minus, so I can say this is x1 and x2 like that. Okay, these are capital X, so okay, and I can say xi, x I1, xi2 like that is the index of that. So these are the two feature, x1, x2. Then I can possibly use my 2-dimension over here. At one axis I can put my x2, and at one dimension I can put my x1. So the actual decision boundary, this actual decision boundary, so let me write it over here. The actual, I will write dB for decision boundary, actual decision boundary. It looks something like this. Let's say an example, x1 equals to x2 square, because as this is a quadratic equation, so I'm writing this complete thing in this way. So let's say this is the x1 equals to x2 square plus 5. This is a quadratic equation. Beside this, it is a parabola, so that's why I'm writing like this. And why I'm writing this is because if you see the parabola, if you have seen the parabola, then if I have a parabola looks like this, then I can equate it. Equation looks like y equals to x square. This is the output, and this is the independent variable on which the y is dependent. So if my x square looks like this, u-shaped, it looks like this, then I can if I want to reformulate it, then I say write it in terms of x1 and x2, these, okay, these x1 and x2. If I want to write this y equals to x square in x1 and x2 in terms of that, then I can say y is my nothing but x2, and my x square is nothing but x1 square. You can see this is y, can you see this, and this x2 is this one. Okay, so now I had written in terms of x1 and x2, and I can if you see the thing over here, then I can just what I can do is I can just substitute over here. So what I'm gonna do is I will say x1 equals to x2. So I just substitute, or not substitute, I just rearranged some equation. So now this u-shaped, if it is in the vertical direction, then this equation is going to give me a horizontal u-shape, and this horizontal u-shape is if you please refer this diagram here, can you see this is a horizontal decision boundary, and it is exactly looks like this. So this is my particular equation that I am looking for. Okay, this is my particular equation, and this equation is exactly similar to the actual decision boundary. And what is my actual decision boundary? If you see, it is x1 equals to x square plus 5. This is the actual decision boundary that we had assumed. So can you see, it is now equal. So x1 equals to x square, and it is exactly looks like this. Just the phi is nothing but constant. If you just put your hand on that plus phi, then the equation looks like this. So that's why my decision boundary is this parabola, and above is also parabola. So now what I want to say is what basis function is going to do over here. So if you observe, to if I'm going to write it over here, I will just separate this out so that my topic is going to okay, so from here we're gonna understand basis expansion, and we are still on the higher dimension, and we are doing something on this basis expansion function to lower down my decision boundary. How to increase this? Okay, so now let's say for as I told you that my x1 x2 is in 2 dimensions. So if I say 2D for 2 dimensions, so for 2D, I have my capital X, and it is having x1 comma x2. This is what we had seen. So if you see, this is in lower dimension, right? And in basis expansion, what we are saying is we want to increase this lower dimension to the higher dimension, but still. So if I'm saying lower dimension, then it means linear model. If I'm saying higher dimension, it means nothing but a non-linear function, right? So what exactly I wanted, that my this linear function moves to the non-linear function but still retain the property of linear. Okay, so you're getting it. So if I want to move my so what I mean to say here is I'm moving my lower dimension to a higher dimension. That means I'm moving my linear function to a non-linear function, but still this non-linear function should retain the property of the linearity. Okay, so I have 2D capital X equals to x1 comma x2 with low dimension, then I must have some function phi x which should be in the non-linearity. So this is going to be my higher dimension. So what I'm going to do is I make x1 comma x2, these are my original data. Then I'll say I'll put some non-linearity over here. So I'll say x1 square and then x2 square, and then let me these are okay, yeah. And then what I'm going to do is I'll say x1 and x2 again. Okay, so this is going to be what I did is actually this is in the combination of x1, so it is a multiplication. Okay, so this is a multiplication. So what I did over here is, if you see that now it is in the higher dimension, this is higher dimension, and the important property over here is that this high dimension retain the property of linearity. Okay, so we move from lower dimension to higher dimension, but this higher dimension still holds the property of linearity. Still they have non-linear functions. So you can see if they have the quadratic equation, but still it will work according to the linear. Okay, so if you what generally it gives you a conclusion over here, small conclusion. So it says if you have two features, if you have two feature, in our case x1 and x2, you can use anything like x1 square, x2 square, x1, x2, and so on. Okay, so you can use, I'm so sorry, and so on. You can use your own mathematics there to improve this x1 and x2 to non-linear. Okay, so for the new page, I'll again rewrite this whole idea of lower dimension to higher dimension. So actual data, that is x, is in 2 dimension. Now we are using basis expansion. It expand it, so it says, so the meaning of this basis expansion, the function, it is so phi x is your basis expansion function, right? So it expand the original x and use basis expansion. That gives you x is in 5D, that is x1, x2, x1 square, x2 square, x1 and x2, right? So you can see 1 2 3 1 2 3 4, and this complete set is 5. Okay, so now this is in 5 dimension. Okay, so earlier it was in 2 dimension. however we use this basis expansion, it expands this x. Actually this x is now 5x. Okay, so this is the function, basis expansion function, and now your 2 dimension get converted into 5 dimension, and you can see this is the punch, and your x here it looks like x1 and x2 only. Okay, so this is what we did. Here let me write it down. We are expanding this actual data using phi of x. So instead of just using x1 x2, now go down, and now we are using expanded feature x1 x2 quadratic x2 x2 and x1 x2. Okay, so this is what we see, and in normal terms you can still write in this way mathematically. X equals to, if it is x1 and x2, that it belongs to the dimension 2, but now your phi of x is x1 x2 x1 square, just x2 square x1 multiply x2 belongs to R5. I hope you are getting this. And this phi x retain the property of linearity, and you can see that why it retains the property of linearity. Okay, and I'll show you why it retains. So make sure if you remember this, that my x belongs to 2 dimension. I am using basis expansion to expand this actual data, and it is expanded with the help of this phi x, which is a basis expansion function, and I am moving this, or I am moving this linear data points to non-linear data points now, and it is in phi d, but still it is retaining the property of linearity. Okay, and why I am saying that is, let's say we do some maths here. So say I have an equation, quadratic equation, x1 minus x2 square minus 5, which is nothing but, if you see, this is my actual decision boundary itself, because I told you that x1 equals to x2 square plus 5, which is my actual decision boundary. If you remember, I just rearranged it to this equation. So this equation, remember this, right now this is the equation, and it is in quadratic equation, in 2 dimension. Okay, this is also, you remember, we represent this equation, as, so I will now represent this complete equation in the term of y equals to mx plus c, which is linear model. So now this quadratic is going to move to linear equation, and I'll use some mathematical term. Mathematically, now this whole thing I'm going to mathematically rewrite y equals to mx plus c. I'm going to rewrite it, and I'll say w phi of x plus b equals to 0. This is my rewritten y equals to mx plus c. So here m is nothing but w, and x is nothing but phi of x, plus this c is going to be in my b. Okay, so this m is going to be your slope, or you can say the coefficient, and this is going to be your y-intercept. Okay, so this equation is a rewritten equation of this y equals to mx plus c now. Okay, now I will say my w What is this W? W is basically nothing but the coefficients, right? And if you see here my equation, I'm going to write here, this is the equation itself, x1 x2 square minus 5 equals to 0. This is the equation, remember. So here the coefficient are here it is not visible over here, but these are the coefficient values, right? These are the coefficient values. So these are nothing but W, right? So my W here, according to this equation, it is the set of, let's say, 1, because x1 is having coefficient 1 here, and then the coefficient for other is going to be 0, then 0, then minus 1 and 0. Okay, so this is these are the coefficient values from this equation, x1 minus x2 square minus 5. Okay, and my phi of x, where is it? Okay, phi of x here. Phi of x is, you already know that it is x1 x2 x1 square x2 square x1 x2, you already know that, and the b is nothing but minus 5. Okay, so I hope you are now getting it. So if you observe the similarity, that my y equals to mxc is, I can write this x1, this quadratic equation in the term of linear equation. Okay, so now your two-dimensional data is embedded in higher dimension feature space, then we use a linear classifier. So this phi of x, this is your basis expansion, remember, this is your basis expansion, which gives you the nonlinear function, still holds the property of linearity. And why I'm saying linear, because in the set itself there is the original data point. If you see, okay, these are original data points which is there in the data set itself of x. So this complete set phi of x retain the property of linearity. Why? Because it holds the original data points. Okay, so that is why we are saying that we are expanding our lower dimension to a higher dimension, but still we are retaining the property. Okay, and now in a more general term, I'm going to rewrite everything. This is just for an example. We are taking the example of this x1 minus x2 square minus 5, but in general terms we don't have two dimension, but we have d dimension space, right? And for the next slide, I'm going to for the next note, actually, for the next note I'm going to give you the expansion of d dimension space, not the two dimension space. Okay, so let me just, okay, so we will see the d dimension space. One more question, if question arises, like from where this set comes from, 1 0 0 minus 1 0, then this set is going to be compared with this phi of x. So if you see, we have x1, then in this equation we have x12, and the coefficient of x1 is 1, and that's why I have 1 over here. And if I have x2, then you see I don't have any component x2 in this equation, so that's why I had put in 0. Then we have x1 square, then if you see in the equation I don't have any x1 square, so I'll again put 0. Then if I have x2 square, then you can see I have x2 square, and the coefficient is nothing but minus 1, so I am putting minus 1 over here, and I don't have any component that says x1 dot x2, so that's why I had said it is 0. Okay, so that's why I have a w looks like this. So I hope you understand it, that I have earlier I have a quadratic equation here. This is a quadratic equation in two dimension, and now I have a newer equation. Where is it? Yeah, this newer equation, the expanded equation, it is in 5 dimension. Okay, and still holds the linearity property. Remember this, linearity still holds it. Okay, so in the next page I'm going to tell you about if we have original data with quadratic term in D dimension. So let's say I have x1 square, x2 square till xd square. Okay, and then if this is the original data, then in d dimension what I'm gonna do is I will linearly combine the terms of this x1 square, x2 square, so I can form new things over here. Oh, my arrow always going to be look like this. So what I'm gonna do is I'm going to change it a little. So let's say this is the combination of x1 x2, and then I'll say x1 x3, and I'll do like this till xd minus 1 to xd. Okay, so this combination is having linear components as well as non-linear component. Okay, so not this actually, let's say this. I'm going to do is this is converted to this, and now this both data or feature space is going to be converted like this. So this is going to be my phi of x. Let's say this whole thing is nothing but, let's say this whole thing is my capital X. Then this is in the lower dimension, and this phi x is going to be now this phi capital X. Okay, this phi capital X is going to be a combination of like this x1 to xd, and then x1 square till xd square, and now it is a combination of x1 x2 until xd minus 1 to xd. So can you see this is phi of capital X, and it is in high dimension, retaining the property of linearity. So now this phi x, this basis expansion, is the combination of original data points. Can you see this? We have x1 to xd, this is one set. Then we have x1 square, which is there, and it is till xd square, and then there is a combination of x1 x2, which is this x1 x2 till xd minus 1 xd. So this is the whole complete set, having different varieties of set, or those sets are linear, those sets are non-linear, but still the complete feature space is going to be high dimension non-linear function, but still retain the property for linearity. So I will write it down here that this feature space, we have original data 2, and its higher dimension 2, and its higher dimension 2. Okay, so I had written x1 and also x1 square, so both of these things are there. And to briefly conclude it, what I can write it down here is, let me change a little color over here and bold. So in conclusion, what I can write down here, any boundary in quadratic, not only quadratic but any polynomial, any boundary in quadratic in x is actually linear, right? In these expanded feature in phi of x. Are you getting this? My x is actually quadratic, however when I do phi of x, I'm expanding the x, then still it holds the property of linear, right? And your linear expansion looks like this. So your linear expansion, mathematically a linear basis expansion, it looks like this. So I'm going to write it mathematically, f of x or phi of x, you can write anything, sigma of from m equals to 1 till capital M, this is actually m, okay, and it is beta of m, h of m, and x. And here the beta of m is the coefficient of x, and the h of m is the mth transformation of x. So this whole thing is nothing but transformation. H of m is nothing but the mth transformation of x, and this is nothing but coefficient of x. In general term, it is, I mean, if you had done linear regression in my session, then it is nothing but theta. Okay, so this is your basis expansion. I hope you understand it. If you have any doubt, you can check me out on the comment section. I'll be happy to help you. Thank you so much.